Thank you so much for coming. Since I see a few new faces, I'm going to introduce myself. I'm Jillian Epstein, the outreach coordinator for the Cornell Astronomical Society. And thank you so much for coming to our special Yuri's Night lecture. For those of you who may not know, Yuri's Night is celebrated annually on April 12th in honor of Yuri Gagarin, the first man in space on April 12th, 1961. Coincidentally, it also celebrates the launch of the first space shuttle mission, which was 20 years later on April 12th in 1981. That is a complete coincidence, though. It was supposed to launch 2 days earlier and got delayed. However, for our special Yuri's Night lecture, we have Professor Mason Peck. Professor Mason Peck is the Stephen Kuj. You're going to have to say it, sorry.
It's not Bart Fried, I think it was. No, it's Stephen Fujikawa, 1977, Professor of Astronautics.
There you have it. At the Department of Mechanical and Aerospace Engineering, his research focuses on spacecraft system architectures, altitude dynamics and control, and the organizational practices for technology development and innovation. And without further ado, take it away.
Спасибо. Привет и добрый вечер. Меня зовут Mason Peck. Это Yuri no Notch, and that's about the extent of my Russian. But I feel like we should at least pay a little bit of homage, a little respect to the first person in space. And that was my attempt, having not spoken Russian for a long time. I'm here to talk about how to thrive on the moon. But given the comparatively small audience, we have the opportunity for a little interaction, which will be fun. So please ask questions at some point. For the moment, let me talk a little bit about the moon and things you care about. I'm coming at this from an engineering perspective. So at the very end of this, we'll have a conclusion of something like, what would you do on the moon? Why would we go there in the first place? That's not a question I'm going to try to address right now. Instead, I'll talk about the how, not the why, or the what that we do. So things we need to worry about on the moon. We need to worry about breathing, drinking, and eating. In fact, this is roughly in order of, let's say, priority, or at least temporal priority, what you need to pay attention to first. Clearly, not breathing in a few minutes, you're done for. Not drinking in, I don't know, 3 days, you're done for. Eating, maybe a month, you're done for. Staying warm is another one. Avoiding radiation is another. I say stay clean, and specifically, I'm thinking of dust on the moon. And there's a lot to say about dust. It might seem like a bit of a boring old topic, but it's not. Another thing you would do that you probably have to do is build on the moon. Then you have the opportunity to discover and ultimately thrive on the moon. So that's what this is about. You could argue that the first 5 or 6 topics are about surviving, but the last one is thriving. So let's start with breathe, drink, and eat. So here's some crusty old pictures. On the left, this is some of the food that was scheduled to be carried on the Apollo 11 lunar landing mission. From left to right, there's chicken and vegetables, beef hash, and beef and gravy, not a vegan-friendly environment. In addition to the kind of weird old exposure and color film, I think we'd also agree those are not particularly palatable looking. That's the way it was for a while. Every now and then, I guess I think about the science fiction aspects of what I do professionally. I am interested in the future. I'm also interested in the future that we can believably anticipate. So science fiction is great as maybe guideposts, guidelines, frameworks, but we don't necessarily take all of it seriously. One of the things you may remember from some distant old science fiction movie is the idea that astronauts would sip food through straws, some kind of liquidy goo or something, because clearly that's what the future holds for all of us, is sipping goo. Well, that has never been the case for space. And these days, this is on the right, vacuum sealed space food, including a beef steak, spinach, a cookie, so some vegetables, which is nice, and an orange grapefruit drink for a habitat designed by Lockheed Martin, probably the largest, certainly one of the largest spacecraft prime contractors in the nation, in the world. Distinctions that you see are certainly color, but also things we've learned in space about food over the years, thanks to decades of space shuttle experiments. By the way, I was around to see that. I was not around to see Yuri Gagarin. So that puts me in a 20-year window somewhere for your information. So we have learned that one thing that happens in space is your vestibular system, certainly in zero gravity or microgravity, gets a little messed up. So pressure builds in your sinuses in your head. And one of the consequences is you don't taste things as effectively, or at least in the same way as you do on Earth. That means space shuttle astronauts historically have preferred spicy food. So Mexican, Italian, other things that can be tasted really well. They're less interested in sort of bland, I don't know, turkey sandwich or something. They're much more interested in anything tasteable. We've also discovered a thing called menu fatigue, which is probably what you've encountered every time you open the fridge and see that macaroni and cheese been hanging out there for 5, 6 days. You're like, I really don't want that. It still tastes good, but I know I don't want it anymore. That also happens to people in space. So menu fatigue and not eating gray lumps has driven us towards something else. And it's roughly what you see on the right. And I'm going to say that represents the pinnacle of space food. I think instead, in the future, putting on my science fiction hat, we will not see that kind of stuff, but we will see, surprised, the same stuff we see on Earth. We'll see it that way because we will grow it, and maybe we'll even ship it from Earth. You know, it takes about 4 days, give or take, to get from Earth to the moon, and that's probably similar to what it takes to ship something from South America to Central New York. So not surprising that we could expect to have imported food, blueberries, for example, in winter. Now, so food is one thing, and I'm suggesting we'll grow it on the moon eventually. If we don't, it's because we have never seriously settled the moon, and it's true for Mars too. If we want to be serious about becoming a multiplanetary species, about a future in which humanity is always in space in some form, we have to learn to live off the land, so to speak, live off of what's out there. And one of the things that's out there, fortunately, is water. In fact, that's another lesson we've learned in the last 30 years. Other planets and planetary bodies are much more like Earth than we might have thought. We might have thought that the moon was just a dry lump full of toxic chemicals and a horrible radiation environment. It's not really that bad, and more to the point, there's lots of water. And that's what this image is meant to suggest. In fact, can we turn the lights off or down or something like that? We could see this a bit better. Figure that out. So what you're seeing here is the density of neutrons on craters on the moon. There are many places on the moon where you see this. This shows something like the density of water on the moon. It's an indirect measure. We're still not completely sure exactly where the water is and in what quantity and how convenient it is to get at, but it's definitely there. And it's there because it's also on Earth. You know, it started off, we believe, the moon started off as a chunk of the Earth, probably broken off at some point in a distant past. So whatever was on the Earth at that point is probably on the moon as well. Except that, of course, on the surface, without an atmosphere, whatever is there probably evaporates or maybe evanesces in some other way, sublimates. So the ice that's there or the water that's there is subsurface, but maybe not too far down. It's similar on Mars, by the way. Dig it down a meter or so, you're likely to find some kind of water ice. It might be infected with perchlorates or other horrible chemicals, but it's still basically water. When you have water, you have virtually everything you need for life, for rocket propellant, for thermal control, for all sorts of things, including growing food. So knowing that there's water nearby is key. One place you find water, as you can kind of see in those craters, it is in fact in the craters, right? So there's reason for that. One is that when a meteor or something strikes the surface, it blows away the regolith. That's the grainy sand, the dust that covers the lunar surface, and then exposes more of that water ice. Or that's how the water ice got there. For example, if a comet hits the surface of the moon, that comet being mostly ice or often mostly ice, strikes the surface and the ice stays there. Probably a lot of it sublimates quickly in the sun, but a lot of it also stays underground and stays there for a good long time. If only there were a place on the moon where sun never shone. That seems like a crazy idea, right? On the Earth, the sun shines everywhere at some point. I mean, maybe not inside a deep cavern in the middle of under the ocean, but you know, basically the sun strikes everywhere. Not true on the moon. There are so-called permanently shadowed regions, PSRs. In those permanently shadowed regions, there is very possibly surface ice, or in any case, subsurface ice very close to the surface, to the point where it's trivial to mine that stuff or extract it, you could say. So these permanently shadowed regions are what they are because the moon is in an orbit roughly around the Earth. It's roughly in the ecliptic plane. Imagine that the south pole of the moon always stays roughly in the same orientation relative to the sun, again, an approximation. But for certain craters, the lip of the crater, the edge of the crater is high enough, or in the south pole kind of dips down low enough that it blocks the sun. So there will always be a shadow in certain places. Somewhere in Shackleton Crater, a huge area, some of those permanently shadowed regions, you can find water for as long as you probably need it. So this is interesting. It's something we hadn't known without lunar science. The Lunar Reconnaissance Orbiter, which gave us this picture, was one of the spacecraft that did this. Another one was from the India Space Research Organization, ISRO, had a very successful mission discovering water on the moon. The very first was Clementine, a mission that did neutron spectroscopy of the moon and was also funded by a classified government organization to try some stuff out. Had nothing to do with the moon, but they thought this would be a cool way to spend the money. So thank you to those guys. Water, I said, gets to the moon in lots of different ways. Again, a little hard to read this, I suppose, but it's from several things. I mentioned comets and asteroids. There are interplanetary dust particles and micrometeorites, little bitty things, pieces of water ice and other stuff that land on the lunar surface. The solar wind brings some hydrogen, and in sending it at high speeds with impacting into the regolith can produce water, among other things, including OH. Volcanism is another. So any past volcanoes on the moon can produce, or did produce, some lava that flowed up and brought with it water in some form or another. So there's lots of different ways in which this can happen. There is a whole cycle of water and hydrogen and oxygen on the moon. It's a little outside the scope of this talk, but if we were interested in extracting water from the moon, it's not as hard as you might think. And that's kind of the message. Now, stay warm and avoid radiation. In fact, I brought a little demonstration in here. See if I can get it. So staying warm on the moon is important, right? During the day, the lunar surface can reach maybe 70 degrees Fahrenheit, which sounds good and comfortable. But remember, there is only, maybe even hotter, depending where you are, there is only radiative heat transfer, right? There's no atmosphere to speak of. In fact, what passes for an atmosphere really is just electrostatically levitated dust, the so-called photoelectric effect from the sun. Where the heck is that thing? Oh, there it is. All right. The photoelectric effect causes electrons to pop off of items, molecules on the surface of the moon, and in doing so, imparts a positive charge to the lunar surface, right? So electrons are negative, so you remove them, you're removing the negatives, you're adding a positive, so the lunar surface charges positive in the sunlight, and lots of very, very small particles, dust particles in particular, levitate in that electrostatic field. It could be centimeters to maybe meters in some cases of a very, very fine layer of dust, but it's not an atmosphere. And since there is no atmosphere, all you get is sunlight warming things through radiative heat transfer. And of course, things cool exactly the same way. So if you are standing near the lunar surface, you feel reflected infrared heat, the heat waves from the surface, you feel the heat from the sun, and you can get quite warm, but it's not because there's a warm breeze blowing on you. And then at night, it drops down to cryogenic temperatures. And by night, we mean the roughly 14-day long period of time where the surface of the moon is not exposed to the sun. So you appreciate that the moon orbits the Earth, right? If this is news to you, maybe you're in the wrong place. But the moon does orbit the Earth, and in doing so, because it's tidally locked, that is, one lumpy side of the moon stays stuck in the gravity well of the Earth and points toward it all the time. The moon rotates at a period of exactly 1 month, rotates inertially in a period of 1 month. So in a month, it's exposed to the sunlight for 14, 15 days, and then exposed to not the sunlight in 14, 15 days. Any place on the moon that is true, except for the PSRs, the permanently shadowed regions, where it's always effectively nighttime. So staying warm, you got to stay warm somehow. A spacesuit will help, but a spacesuit is very much a temporary thing. Most spacesuits can't maintain an astronaut's living conditions for more than a few hours. So if you are dropped off in space, that's probably the end of you. Instead, you have to exploit the resources you have available. And that was my message earlier, live off the land, right? So how do we do that? Many ways to create heat. There's nuclear power, which I feel is expensive and unnecessary. There is just plain old geothermal power, which feels like a really good idea, but no one's looking into that very deeply. Essentially, what it would require is that you use some kind of working fluid. Maybe it's the dirty water you find on the moon. You pass it down low on the moon to maybe store heat during the day. You bring it back up at night, or use it for cooling in the reverse way. So some kind of thermal transfer with fluid using geothermal energy might work on the moon. But the obvious answer, honestly, is just to hunker down in a habitat and cover yourself, or cover the habitat, with regolith. lots of sand and rocks and whatever. And that is what our ancestors did thousands of years ago, and it's what we would probably do tens to hundreds of years from now. That'll keep you warm, but we also can use modern day engineering to make that a little bit better. So in this box is a substance called aerogel. Anyone heard of aerogel? Raise your hand if you have heard of it. If you took MAE 4160, you probably heard of it. It is the least dense substance that we know of. It's a substance that's formed as a kind of silica gel, so it's kind of like a glass foam, if you like. And apparently they make it by dissolving silica in some solution, then they remove the solvent, and then you end up with this porous structure. If I'll pass this around, please don't open it. What you'll see in there is a little foam thing that keeps the aerogel in the box, but under it, that bluish substance, that is the aerogel. You can barely see the edges. Sometimes they call it solid smoke. It is so low density, but also so insulating that apparently if you built a house out of this stuff, or just, used a layer of aerogel 1 centimeter thick, the light from a single candle would be able to keep that house heated in the winter. That's what they say. There's other ways of measuring that too, but I'm not going to get mathy about that. So you can pass this around, take a look at it. It's fascinating stuff. So aerogel is one answer to keeping you warm. By the way, you can also buy aerogel insulation right now. You can just go online and not just the pure stuff, you can buy that online too, but I mean, you actually get sheets of it that's built like insulation that you would have in your house. It doesn't work that much better, honestly, than other stuff, but it is interesting to try to commercialize it. Okay, so you stay warm with that. It is also true that the radiation helps keep you warm. So the radiation can be a risk, but regolith will help prevent that risk from being a problem. But there are other ways to go. Rather than piling up all this dirt over your habitat, what could you use that's already in place? Again, the theme being live off the land. Well, one is lava tubes. So a lava tube forms, and they form on Earth as well. Anytime a volcano erupts and sends lava streaming down terrain with a certain density, it can melt that terrain and drill a hole through it until finally the energy is lost and it peters out. But these lava tubes on the moon can extend for many, many, many kilometers. Again, true on Earth, true on Mars, by the way. Nice thing about lava tubes is they sometimes can be airtight. So you seal up the one end, and now you have a ready-made pressurizable tube in which you can do whatever you want. There was a book years ago, The Moon is a Harsh Mistress by Robert Heinlein. Heinlein being one of those golden age science fiction authors, really clever, also really deplorable in lots of other ways. So read the book and also hold your nose while you read it, but it's really interesting. One of the suggestions he makes is perhaps mining out or sealing up a lava tube and then putting some power in, or at least maybe light tubes from the surface would be enough to grow crops. And so this would be a way to create a greenhouse on the moon without really having to invest in structure and build all that structure. What you see on the left there is a picture of a collapsed lava tube on the moon. So you can see this kind of indented, it's like a worm trail, so it doesn't have anything to do with Shiverwood. It is in fact a collapsed lava tube. And on the right is kind of an artist's depiction of a satellite looking down into a lava tube from the surface. So lava tubes, a ready-made habitat perhaps. I'll keep you warm, keep the radiation off your back. But there's much more to constructing stuff on the moon, and that's why NASA has created the so-called Lunar Surface Innovation Initiative. That's been around now for 6 years. It is an attempt to invest in technologies that will enable a permanent human presence on the moon. And there's a wide variety of areas in which they're investing. You can go look it up under LSII, but I want to emphasize just a couple here. So one of them is the area of excavation, construction, and outfitting. Now, there are disagreements about how to pursue this stuff, and that's because people are enthusiastic, right? We'd love to do this, and we want to be sure we're doing it the right way. So lots of ideas. Some are probably good, some probably not. Excavation, construction, and outfitting, or ECO, is the general set of problems that involve digging holes and building stuff, okay? And there's a wide variety of activities. NASA also adds the word autonomous to this. The implication being that maybe you could send some robotic systems before humans, and they would autonomously dig holes, make flat areas, build up berms, or whatever it is that might be interesting. I mentioned building up berms because despite the value of those permanently shattered regions, we could make our own as well. We could just make a very deep hole or a very high walled structure somewhere near the poles, but not necessarily right at the poles, with the same kind of benefits. So that's an interesting possibility. Anyway, autonomy or autonomous, that would imply that these robots are programmed to do this, or maybe they're encouraged from the ground, the way the Mars rovers, I'm sure you've seen, can explore the surface of Mars. But it's asking a lot, and these rovers would not be very big. There's a competing school of thought that says very likely people will be happy to go to the moon, and it might even be possible for them to operate what amounts to terrestrial construction machinery on the moon. I mean, after all, we have well over a century of designing front-end loaders and backhoes and just all sorts of stuff that could be used for lunar construction. How hard would it really be to make those work on the moon? Pretty clearly, you can't run a diesel engine on the moon, right? Or any kind of internal combustion engine. It requires about 13 times as much oxygen by weight as it does gasoline. That works great on the Earth, but not so great when there's no oxygen. So instead, probably power with electricity, probably solar power. Anyway, those robotic systems could do the job, but maybe more, as I'm suggesting, likely we would just go to Caterpillar or John Deere or Kubota and buy your favorite tractor and set it up to work on the moon. Now, all of these suggestions sound a little nutty because you're thinking, well, when we build Mars rovers, we watch every single gram of weight and they got to be super reliable. Well, I'm here to tell you that's not necessarily what the future holds. And I'm going to zip forward just a bit to make that point. There is a vehicle on the horizon called the SpaceX Starship Super Heavy. Now, I'm not saying anything politically here about Elon Musk, so just set that aside from your mind. Instead, I'm talking just about the technology, which is transformative. This rocket is capable of sending somewhere between 150 and 200 metric tons, so that'd be 200,000 kilograms, to the surface, Earth orbit. Furthermore, it's designed to be refuelable, as I'm sure you've seen in some videos, right? You've seen these things land on the Earth and then take off again. The fact that it's refuelable means you can do another thing that Robert Heinlein and Arthur C. Clarke commented on years ago, which is once you get to low Earth orbit, you're halfway to anywhere. This is a calculation based on the math of the gravity well of Earth. It takes something like 10,000 meters per second of delta V or rocket acceleration to get to low Earth orbit, and from there about the same amount to escape, or even get to the edge of the solar system. So that's kind of an exciting possibility. If you can do that with the SpaceX rocket and then refuel it, you've got a lot of propellant that can take you to the moon and even back. So another thing about the Starship is not just its size or scale, not just the reusability per se, but the fact that reusability makes it low cost. With Starship, the prediction is it'll cost you less to put a kilogram of mass into space than to mail it from the east coast of the US to the west. So it's more expensive to FedEx something than to send it into space. I think that's a fascinating possibility. And that opens up so many things. It democratizes space, first of all. But it also means what we used to take seriously in terms of making spacecraft super reliable and super lightweight, it just doesn't matter anymore. You can think about space systems very, very differently. They can be disposable. You can make them out of iron and concrete. In fact, there's been a proposal to take a 5 or 6 meter terrestrial telescope with all of its rust and paint and bits of moss and other junk and concrete on the base and put it in the Starship and put it into space. And you would end up with something like the Hubble Space Telescope for on the scale of a couple $100 million. So that would be a factor of 100 cheaper. Even if you don't get the same level of science as you get with Hubble, let alone with James Webb, the fact that you have 100 of them, it's a game changer, right? So I'm very excited about the prospects of something like Starship, and I hope that company keeps doing its thing. That outcome seems like it's less extraordinary when you compare it to some other rockets in the recent past, but there is so much going on with Starship that I'm not going to get into here that makes it so much more capable that there's almost no comparison. $10 to $100 per kilo in steady state. I don't know when was the last time you mailed a package to a friend or relative across the country. That's probably about the price you paid, you know? And yet you could do the same thing and put your object into space. Whether you could do that kilogram at a time is a whole other story, but at least at the scale of dollars per kilogram, that's what we're talking about. Also, the expectation is the Starship could do as many as several launches a day. Now, back in the 1980s, we thought that was going to be true for the space shuttle. And that was never true of the space shuttle. In fact, the space shuttle turned out to be the most expensive vehicle per kilogram that we had access to, which is too bad. It was an awesome and successful effort. It was the mainstay of the human space program, but it never really lived up to its potential for a variety of reasons. One of them was that sometime in the 70s, it became clear to the Defense Department and the intelligence community that you could use this to launch spy satellites. So they changed the requirements in the space shuttle from being a lean, small, rapid, quick turnaround, inexpensive vehicle to being a behemoth that could launch something of the scale of the Hubble Space Telescope or James Webb, but defense related or spy satellite related stuff. And the Defense Department used that exactly once. And then there was the space shuttle, the 1985 Challenger disaster, and they never used it afterwards. So we ended up with a very expensive rocket to serve a customer that never bought it. Nevertheless, it was successful in other ways. It was what enabled us to build the space station. So we can't completely look askance at the space shuttle. The Starship, though, is purpose-built for rapid turnaround, high mass, low Earth orbit at an economic price. So I would argue, and others have too, that mass will no longer be a constraint. Those of you who are used to thinking about space and what it means to put a satellite into orbit will probably feel a mix of emotions. One is you feel cheated that for the last N years of your professional or academic career, you've been taught how to minimize the massive aerospace systems. And then you also think, well, gosh, that's freeing. What could I make instead? What would I do instead? And this is a question for you to contemplate. Yours is the generation who won't think so much about mass when they think about spacecraft. So there's other facts and figure here of potential interest. For example, on the bottom, by the way, this is from a company called K2 Space. These are two folks who actually used to work at SpaceX. Now they're building a satellite company to exploit the Starship capability. The cumulative mass that humans have ever put into orbit, ever, is about 16,000 kilograms. The total mass per Starship per year, launching 3 times per week, is 16,000 kilograms. And if you had 10 Starships per year, it could approach 1 million kilograms of mass into orbit. Those figures are astonishing. It's a watershed event, or will be when we have, or if we have, Starship. As an example, let's say you're trying to launch something like the space station. So this took about 100 launches from the space shuttle. It is, by the way, about 444,000 kilograms. It makes me wonder about that figure on the previous page. But anyway, 444,000 kilograms. It's 100 meters across, by the size of a football field or soccer field. It took the space shuttle at $500 million per mission, and maybe more. Again, about 100 missions to get that into space. The Starship could do this for maybe 15 million per launch, and take about 4 launches, cost about $60 million. $60 million is less than virtually any NASA science spacecraft ever. So you could have a whole space station for less than any single science spacecraft NASA's ever built. I'll go farther to say that we are planning another space station. It's called the Gateway. It will orbit the moon. It will serve literally as a gateway. It will be a means by which you can dock with something in lunar orbit and then descend to the surface and back and so forth. So prospect of really high value for science and human space. So that could be done for, again, a similar cost point. Once again, by reducing the cost of mass to orbit and increasing the ability to put mass into orbit, we completely change the conversation of what's possible. So finally, getting back to the moon, why am I bringing all this stuff up about Starship? Because what you may be concerned about is how will we send that Caterpillar front-end loader to the moon? How will I send that massive concrete and steel telescope to the moon? And my answer is, don't worry about it. Use Starship. That's an interesting possibility that we could build stuff now on the moon where we don't worry about mass as much. So when we're building things on the Earth, we don't really worry. Let's say I've never built my own house, but if I were to do so, it wouldn't occur to me to wonder how much it weighs. Right? It wouldn't occur to me. I wouldn't care how much it costs. So I will say the same thing is going to be true for the moon. Just like we would probably grow our own food, we would probably build our own stuff using more or less traditional construction methods. And I'm going to say that the reason that's the right answer is not just because it's cheap because it's the way we know how to do things. right? We know how to live off the land on the Earth. We know how to build stuff like mud huts. And that's probably what we will do, certainly for the foreseeable future, when we finally have a sustained human presence on the moon. This is an example of what you could do instead of James Webb. JWST cost about $12 billion, maybe more. It's a fantastic system, and I'm a huge fan of having James Webb, but also it's expensive. Here's the Big Something telescope that has been proposed. That Big Something telescope is probably the size of James Webb, but look how it fits in the fairing for SpaceX Starship. It is super teeny tiny. One of the challenges for James Webb is it needs to unfold to deploy these mirror segments, right? And that's challenging technically. It costs literally billions to figure all that out. And it works great, so good for us, right? What if we never had to do that? We could just launch a single solid piece of glass, S-glass, or some kind of material that doesn't require any kind of deployment. And what if we mounted it not on some super exotic beryllium aluminum multiple layers of composite kind of structure? What if we just hogged out a big old piece of Invar, which is an alloy that doesn't change due to temperature, right? Well, you'd be done. Almost all of the technical challenges for James Webb would be gone if you had access to a spacecraft that could launch it without deployments and with no regard to mass. So the future might hold dozens of James Webb scale spacecraft, or maybe even more exciting, one as complicated as James Webb, but more like 100 meters aperture. That would be interesting. We might actually get images of distant exoplanets, direct images. So that'd be exciting. One of the ways in which we can exploit something like SpaceX's Starship's capability is through in-space assembly, manufacturing, and in-space servicing, assembly, and manufacturing. ISAM is what it's called. So just a little over 2.5 years ago, actually almost 3 years ago now, there was a policy written by the White House. A lot of us, some at Cornell, had a role in shaping this, that lays out how you can literally build the future in space. Rather than thinking about spacecraft like we think about the Conestoga wagon, where you throw your salt pork and your good old bulldog Jack in the back and you make your way across the Rocky Mountains, and then that's, you gotta live, survive that way. Rather than that, it's much more about infrastructure. It's, now we can drive from here to California in a matter of days, rather than having to take months and risk life and limb, end up eating our friends in the mountains. We don't do that anymore because we have highways, right? What if we had infrastructure like that in space? I don't mean a physical highway, but what if we had all the communications necessary, pit stops to gas up our spacecraft, other ways to resupply ourselves, and then the ability to fix and even build new spacecraft along the way? Once again, that would change the conversation, but it's only possible if it's relatively inexpensive to put those raw materials and that refueling material into space. So that's what this is about. About a decade earlier, we tried something else. We tried seeing what would happen if you 3D printed things in space. This was a complete bust, but that's because it was 2014. Now, 10 years on, it's a great idea. And in fact, there have been, for several years now, 3D printers on the space station. They're more or less the familiar kind, but what about a less familiar kind? This is called Spider Fab. As you can see, it's inspired by arachnids, right? The notion is with the ability to extrude truss elements, so like squish them out as bars or beams, you could interconnect them in space and build something really large without having to worry about the kinds of deployments I was referring to before with James Webb. You could build what's implied here, a very, very large aperture radio telescope, or maybe optical telescope for space, or maybe even a habitat or a structure for folks to live in or use for other purposes. This is what ISAN enables. It enables a view of space that is not just one spacecraft that does one science mission. It is all about building space for all of us. This is a picture of the 3D printer on the space station. So Butch Wilmore is an astronaut. At one point, I don't know when this was, 2015, I think. He complained, I really need a ratchet, I really need a wrench, but I don't have one. I have to wait for 3 months before one gets resupplied to the space station. Well, unknown to him, the folks at, it was called Made in Space at the time, now called Redwire, had put they knew that they put a 3D printer on the space station, but unknown to him, someone discovered that he was interested in getting a wrench, the red wire guys programmed a wrench into the 3D printer and printed it out so that a day later he walked over to that and pulled off the wrench he needed. So they like to be a little exaggerating about what this is. They're saying it's like the replicator from Star Trek, right? You ask for a cup of Earl Grey and there it is, but that's not quite what this is. But what is important is you've already sent the mass up there. It's just in the wrong shape. In fact, that's something we could say generally about all of the resources in space. Lunar regolith, asteroids, comets, yes, they have scientific interest and we should study them, but also they are the raw material of our future in space. Once again, it's just in the wrong shape. So whether it's through spider fab or some yet to be defined massive gantry 3D printer in orbit, or maybe on the lunar surface, we will shape the material of space into a sustainable human future. That's the build part of this. We're reaching the end. Discover is a thing we want to do. You may remember the movie The Martian. So this is a story of an astronaut who was left behind because there was a dust storm, which by the way would never happen on Mars, but whatever. He's left behind and the only communication thing he has goes away, so he can't tell NASA that he's still alive and therefore should be rescued. Instead, he has to go through all sorts of shenanigans to survive, including planting food for himself. He finds some potatoes, he plants them in his own feces because that's what he has, and it makes sense, you have to do that, and more or less grows his future on Mars. Once again, that naughty Mars wind comes and tears the whole thing down. Again, it won't happen. But as exciting and interesting a movie, and by the way, the novel's not bad either, as interesting as that is, I don't think that's the future. Instead, this is probably the future. Nokia, for a number of years now, has had a contract with NASA to build smartphone communications capability in cislunar space. Now, by cislunar, we mean everything that includes the Earth and the Moon. So imagine, if you want, cell phone towers on the Moon or in space. It's both simpler and harder than all that. But in any case, the communications protocol that NASA has been using is based on this idea of one big science mission and then a whole bunch of capabilities on the Earth to support it. Made sense in the 60s and 70s, probably the 80s. It does not make sense now because we have the capability to use smartphones or cell phones, if you like, to communicate in space. In fact, future space communications will almost entirely be using a 5 or 6 or 7G network. That's kind of a fascinating possibility. In fact, you could probably fly your cell phone or your smartphone. It would be able to communicate. It's got sensors, has a camera. It's got what you need. Just add some solar panels. The point is that there is an infrastructure being built for space right now. Communications is the beginning. So that when Matt Damon finds himself needing to eat his own potatoes, that doesn't need to be his only choice. He could just whip out his phone, call home. There's other possibilities in space. If you can build something in space, you can also maintain something in space, and that what you maintain might be a large space station. This is a picture of Orbital Reef. It's an older picture, but a concept from Blue Origin, basically a space business park. Now, over the years, we've wanted the International Space Station to be a little bit like this, but this is a commercial enterprise to try to develop pharmaceuticals and materials and a whole wide variety of other things for use on Earth that are actually cheaper to make in space. Once again, remember, the price per kilogram is dropping way, way down. So it can be cheaper to build things or produce them in orbit and take advantage of microgravity and then sell them on the Earth than just to make them on the Earth using normal processes. So that's one of the things that Orbital Reef could do. Imagine what else you could do if you had the Moon available to you. So in terms of discovery, maybe one thing you discover is not necessarily new lunar geology, as exciting as that would be. Maybe you discover a new way to make a buck on the Moon. So you might discover that there are ways to, I don't know, create jewelry or produce pharmaceuticals, again, maybe even make other materials. And one of those materials is called Z-blan, Z-B-L-A-N. Z-blan is a type of fiber optic. When it's made on the ground, most fiber optics have impurities due to the curing process where gravity kind of screws up the chemical constituents in some way that I don't fully understand. In space, however, with microgravity, the purity of that fiber optic cable is so high that if you were to make it in space, bring it back to Earth, a fiber optic cable user, a telecom company, could string a single strand of that fiber optic all the way across the country without any repeaters or amplifiers. And that would not only save money, it would improve the environmental impact of putting these things around, and would also improve internet speeds. So there is a significant market for something like the Z-Bland made in space. And that's one of the many products that folks are looking at as a potential product that could make you a buck in space. So I'll end there with the following question. If you can make a buck in space, if you can survive in space, you can get your blueberries sent to you whenever you need them. You will be warm and safe and clean. Oh, I didn't talk about the clean part. I'll get to that if you have questions. You can eat, drink, and breathe what you want. What would you do to thrive in space? You let me know. Thanks for your kind attention.
Okay, thank you so much. Do we have any questions? I'll run this mic around so that everyone can be heard. If you have any question, feel free to raise your hand. If anyone on Zoom has a question, feel free to drop it in the chat.
I've answered all questions. That's great to hear.
I was fascinated to hear that you combined aerosol materials. Decades ago, in, I believe, an issue of Fine Home Building, there was a sidebar article on Windows in the future that they would include an aerogel instead of an inert gas sandwich between the aerogel, and you have a window that functions like a window, but has to be wall.
Yeah.
I'm still waiting for the what happened? What did happen?
A couple things I can comment. So for those of you who didn't hear, the comment was, it's been proposed that you could put aerogel in layers of a glass window for use in residential applications and save a lot of power that way. And so it's a great point. So one thing is it's expensive to make aerogel. Not terribly so. I mean, I think that little block I was passing around, that thing was, tens of dollars. I could buy it online. So, it's good for showing in class and whatever. So it's not exorbitantly expensive, but if you imagine a whole window that's probably $1,000 scale, and maybe that's worth it. I am not convinced how transparent it would be. That's the other thing. The piece you saw was translucent, maybe not transparent, not opaque. The other thing that's, let me offer a completely orthogonal comment, okay? Cool question, and probably there are some residential uses that haven't been thought of. One of my favorite offshoots of aerogel is something called sea gel. I don't know if anyone's heard of sea gel. I don't know how it's made, but essentially you can make it similarly to aerogel, where you evaporate the solvent that holds the silicon structure in place. But in doing so, you fully evacuate those little microscopic cells. So no longer do you have air inside, you have vacuum inside. And that makes a solid that's lighter than air. So you can make this, what feels like a piece of styrofoam, you let go and you'll never see it again. That's just a fascinating idea. I don't know what use that has, but I will say that from an aerospace engineering perspective, anything you can do to lighten up materials is probably a good thing. So imagine that you needed to, I don't know, fill the space in a wing with something, probably good to fill it with a lighter than air solid. That's potentially beneficial. Anyway, that's not a housing application, but that's something of potential interest. What else have you guys got?
Hi, thinking about the chart you showed of just how much more mass we're going to be able to put into space with Starship and new technology. Are there any companies talking about plans to deal with possible like space junk and stuff like that?
An excellent question. So the question, if you didn't hear online, that was about space debris. Certainly, the more we put into space, the more of it will become debris. So I think that is 100% a concern and a question to be asked. And it's the same question that we continually ask ourselves and fail to answer on the Earth with things like microplastics and all sorts of other pollution that we produce. We produce it and then we complain about it and we keep doing it. So I think that's probably what the future holds in space. At the moment, well, here's the thing that probably you've heard of. There's a thing called the Kessler syndrome, named after a NASA engineer who asked the interesting question, I wonder how soon it will be before all the bits of debris in space collide with each other, and those pieces then collide with other pieces and continually break up into a huge ring, essentially like Saturn has, of debris around the Earth. I wonder how many thousands of years away that is. And the answer was 0.001 thousand years. In other words, it happens. It is happening. What you can do is look at the number of space debris particles, there's ways to estimate this, and it should follow a roughly exponential curve. You can plot that, and we are well on our way up that curve. So the future that we're headed for is one in which spacecraft need to be built with more aggressive mechanical shielding to prevent debris collisions or micrometeorite, we can call them collisions. But even today, the number of times that the space station or other vehicles have to move out of the way of orbital debris continues to increase. It happens, I think, roughly monthly, that the space station has to perform some kind of maneuver to move itself out of the way of some debris. Now, most of this, in terms of mass, is debris that has, it's there from 1960s and 70s, maybe 80s era rocket bodies. These are the spent stages of vehicles, mostly from Russia, France, and China to an extent, that just haven't deorbited yet. The problem is not that they are there in these massive forms, it's that the mass is there, right? We're not actually worried about being hit by a huge thing, because honestly, any impact of any piece of orbital debris is a game-ending impact. I mean, even something as small as a fleck of paint can destroy a spacecraft, and there are plenty of paint flecks out there. No, the huge rocket bodies, they could be, half the size of this room. Those things are a problem because when they strike something else, they'll break up into more and more pieces. So the argument is that any piece of space debris is a bad piece of space debris. And so it's simply the number of pieces of debris that's the problem. So to your question, how do we think about this in the context of SpaceX and others producing a lot more material in space? Inevitably, it's going to lead to a lot more orbital debris. The question we have to ask ourselves is, does that mean we shouldn't do it? Like if we don't ever go to space anymore, is that the right answer? I mean, I don't have the answer for you, but this is the kind of question you have to ask. It's kind of an existential question. Either we put up with orbital debris because there's no way around it, it's going to happen, or we just don't go to space anymore. Or we reserve space for the exclusive and rare use of rich nations who can do some science missions from time to time and not democratize space, but I think we're heading. But yeah, that's a great question. I think the answer is going to be something like there will be international treaties and regulations. At some point, some big objects can just plain blow up and it'll produce a bunch of debris unintentionally. But that unintentional stuff is one thing, and we mitigate it to the extent possible. Instead, there have been intentional attempts to create space debris, believe it or not. Early on, the US exploded nuclear weapons in the Van Allen belts for various scientific reasons. Also, in the recent past, China twice blew up some spacecraft just to see what would happen, and also as apparently kind of a military threat implied that they can do that to this thing, threaten other people. But the problem with those experiments is that they produced a huge amount of debris. The very small particles tend to enter the atmosphere very quickly because it's a cube square law kind of a thing. The mass is very small compared to the surface area, so drag, solar pressure, other effects that slow things down as they travel are very pronounced on the small bits and pieces. But the big stuff sticks around. Big stuff being, I don't know, the size of a chair or a desk or something. That'll be there for hundreds or maybe even millions of years. And again, the big stuff is a problem because when it collides with other big stuff, it produces more particles of debris. It's the sheer number that ultimately matters. Well, we can keep talking about this, but I think you're onto a key question, which is the international community, including the US, we all need to come up with some understanding of how to mitigate space debris in our use of space. Now, there are rules and regulations about this. Not everyone follows them, but it's something to be taken seriously, and probably there are ways to govern orbits to make this work a little bit better. When I was at NASA, and this was in 2014, we worked on what we secretly called the orbital bike lane. This never actually happened. But the notion was, couldn't we create a particular orbit that doesn't significantly intersect other orbits we care about, like the space station or commercial orbits going to geostationary or whatever? Couldn't we create an orbit where we can do experiments, people can launch their CubeSats and do all sorts of other things, including these military experiments that I guess they need to be done? Couldn't we do that and just relegate it to that particular orbit that becomes a place where that happens? So just like a bike lane, it's cordoned off from the main thoroughfares of space for a very specific purpose. And we called it a bike lane because we were kind of emphasizing the small sat casual university or student use of that, but honestly it would be appropriate for anyone doing that. So One way to do it is through regulation that creates, bounds on orbits. Once again, who's to say that people will not just ignore those and do what they want? I'm sorry, it's a long answer to your question, but I appreciate it. Thank you.
You mentioned, the sea gel that's lighter than.
Sea gel, yeah.
I know it's obviously less of an issue with the super M, but do you think there would be merit, I guess if it's even possible, of sort of creating sea gel here, shipping it up there, and then making it into either aerogel or medium sea gel to use as installation on the moon or elsewhere in space?
Yeah, that'd be true. That'd be true for sea gel or aerogel. I mean, the reason you have to like sea gel is kind of an oddity because it's lighter than air. But in terms of density, it's not much lighter than air, and aerogel, which is easily done, and you've seen it because you have it in your hand, that's, probably just as good. So no need to use sea gel as such, but aerogel, generally, it's a great way to go. I didn't mention this, but it's also extremely thermally insulating. You can hit that with a blowtorch, and on the other side, you can just touch it. It's not a problem. It's extraordinarily high performance. So I did mention that in the context of staying warm, but it does all sorts of other cool stuff as well. So yeah, that's a useful thing to use. A thing that is done today, routinely, rocket fairings, that's the kind of shroud that covers the spacecraft when it launches. Rocket fairings are purged. That is, they remove whatever they can from them by pumping something in. Now, sometimes it's just plain old nitrogen, which removes oxygen and humidity, which is probably a good thing for the spacecraft. But sometimes they use helium, exactly for the reason that sea gel is kind of cool. Helium in the shroud of a rocket makes it lighter, and you still have pressure in there, so it actually structurally works well. If you fully evacuated it, which would be the best thing to do from a mass perspective, there'd be a risk of the fairings collapsing inward and crushing everything. So there are ways to make rockets lighter using low density materials. Here, I'll leave that.
So like you've said that we basically have all these plans, of what we're gonna do to private space, but like how realistic is it have this happening in like the near future, and like what's like the roadmap looking like, so to speak?
That's a wonderful question. So one of my jobs at NASA was developing the technology roadmaps for NASA. So that was an interesting job. One where I think we had some fairly clear ideas of what we would want to do, but it was very difficult to navigate the politics of getting it done. Everyone has their pet ideas about what should be done, and there's kind of the right technical answer, then there's the right answer because it's, built in Alabama or whatever, and whatever. So yeah, there are roadmaps in terms of, and you can actually look at them online on NASA's website. You can see these technical areas. I think there's 17 of them at this point. But they cover all wide range of technologies that can help. In terms of time, it is generally agreed that there is no major technical hurdle standing in the way as long as there is the money to do it with. So if we just had the money, we could be on the moon in a matter of single-digit years with a sustained presence. Now, why does it take money? Well, at the moment, we don't have the technology that can easily take people back and forth to the moon. Instead, we would have to spend a lot of money to do that, but that's where the money comes in. We would have to spend money to condition the lunar surface to make it livable. So I don't mean terraforming. I mean, you have to build the habitats. You got to put in the electrical power grid, the communications towers, the solar panels, and whatever, and that costs money. But really, the technical challenges are not huge. There are definitely better ways to do it, but if we just wanted to do it today, it would just cost a bunch of money. And I'm sorry to say that that's what it comes down to. There are cool ideas on the horizon. One of them is nuclear space propulsion. At the moment, it doesn't really get you any farther than regular propulsion, but at some point, it might be that the efficiency of a nuclear rocket engine would be better enough than a typical chemical rocket engine that you could shorten the trip to the moon and back, and that would reduce the number of consumables, water, air, whatever that you need on the way. It would also make it possible to, for things to be safer. Let's say something medically bad happens to you on the moon, you are probably 8 days away from Earth, because you got to send a rocket, if you can launch it immediately from Earth to the moon, pick up the person on the moon, get him back from the moon. Probably an 8-day thing, maybe less at the moment. And lots of medical issues will not resolve in 8 days. They'll go the wrong direction. So unless you want to build a hospital on the moon, again, that costs a lot of money, you've got to come up with a way to move people or equipment faster. And maybe that's nuclear rockets. At the moment, we don't have a great idea for anything better than that. So I think investing in technology is a way to do incrementally better. But at the moment, there's not a lot standing in the way. There was a 1950s era futurist named Kraft Ernke. He had this interesting quote. If God had meant man to go to space, he would have given us a moon. Now, ignore the sexism and the religious overtones, whatever. The interesting irony of that statement is we do have a moon, and it is a wonderfully convenient stepping stone to anywhere else. So one of the reasons to invest in lunar infrastructure is not only for the moon itself, but because it can be a stepping stone to Mars. So on that roadmap that you asked about, I would say in a decade, it's permanent humans on the moon. In 20 years, it's probably permanent humans on Mars. If we maintain the will and if we can continue to invest. These days, where the economy is going, it's not clear what that future holds, but that could turn around, or maybe private industry will fund that. It's hard to say.
Any other questions in the room?
Can I ask you a question, Josh, or do you need to ask me a question?
Someone ask you one.
All right, go for
Before the talk, I noticed there was a video at the end of the presentation. Can you speak more to that?
I kind of didn't want to play it, but I guess I will for giggles. All right, so in a brainstorming moment, some of us came up with an idea for the future. Let me try that again with sound. Stand by. Sorry, I didn't ask him to ask you this question. And we may not be able to see it. Well. Maybe we'll have to do this afterward. So, sorry. I'll answer your question there. All right, thanks very much for your time, guys. It's been great talking with you.
Yeah, I'm gonna quickly check if we have any questions on Zoom. I think
Okay,
we
yeah, go
do.
for it.
I think both questions asked on Zoom. One of them was, SpaceX can launch heavy, but can it land heavy rockets?
Oh, that's a neat question. So I don't, quick answer is I don't know the answer to that, but it is also the case that the current technology more or less lands with the rocket empty. If the question is based on the assumption that what you want to do is to send a rocket to the moon and then take off again with propellant, I don't think it's designed that way now. But one of the cool things about the moon, because there's so much water, you also have rocket propellant, right? If you have water, you can use electricity to turn it into oxygen and hydrogen, and that is one of the best rocket propellants there is. In fact, an interesting thing about that, of course, is it can be gaseous, and you might be able to build a rocket stage that doesn't need aerodynamic performance, because after all, the moon has no air, right? So you just have these huge gaseous tanks of hydrogen and oxygen taking off from the moon that you make from lunar water. So that's a futuristic answer to the question, but at present, I don't know that the Starship is capable of taking off, landing with a full load of propellant. However, landing on the moon, of course, is maybe easier because it's only got 1/6 of the Earth's gravity. So there's probably some threshold where the propellant that you keep on board is not that much and also would still allow the Starship to land with sufficient load capability. So I don't have the answer to that, but I will bet you some at SpaceX. I should have been thinking about it.
And in the interest of time, I think we're gonna cut it off there. But another round of applause for Professor Mason Peck.
Thank you. Happy Yuri's Day. Yuri no wieczór. How about that? Happy Yuri's evening.
Yes, and as always.